You've got a service that's crashing under load. You add 3 more instances behind the load balancer. The crashes stop. Problem solved. 6 months later, the same service starts dying again. You double the instance count. It still dies. You quadruple it. The same. Welcome to the load balancer trap. I've lived this twice. The first time it was a classic CPU-bound bottleneck. The request queue was growing, latencies climbed, and the health checks started failing. Spinning up more instances behind the load balancer worked beautifully. The traffic spread out, each instance got a smaller share, and latency dropped. We wrote horizontal scaling on the whiteboard and felt clever. The second time, the containers kept getting killed by the out-of-memory killer. The same symptoms, sluggishness, then death, but a completely different disease. No amount of horizontal scaling fixed it. What fixed it was giving every instance more RAM. That's when the penny dropped. Vertical scaling and horizontal scaling solve different classes of problems, and a load balancer can disguise the real bottleneck so well that you'll burn money adding copies of a thing that is fundamentally under-resourced per copy. Let's ground this. A load balancer sits between clients and your service instances. It receives requests and forwards them to the instance that seems healthiest. Round robin, least connections, whatever algorithm you picked. The model assumes all instances are interchangeable. If one can handle 50 requests a second and you need 200 requests a second total, you place 4 instances. That's horizontal scaling. It works beautifully for stateless CPU-bound work that has a predictable per-request cost. But the model breaks when the bottleneck lives inside the instance, and increasing concurrency across many instances doesn't move that bottleneck. It only redistributes the same per-instance stress. Picture a containerized API that builds an in-memory index of a large dataset on startup. Each instance uses 3.4 gigabytes at idle. The pod memory limit is set to 4 gigabytes. When a burst of heavy requests arrives, say a complex join, that materializes hundreds of megabytes of temporary data, the process jumps to 4.1 gigabytes, the kernel's out-of-memory killer wakes up, and the container is reaped. Now imagine you have 10 such pods behind a load balancer. The load balancer sees one pod go dark and reroutes traffic to the healthy ones. But because the work that triggers the spike is request-driven, the next pod that receives the same kind of request also crosses the 4 gigabyte line and gets killed. The load balancer keeps sending requests, and the pods fall like dominoes. More instances didn't fix the underlying per-instance memory headroom problem. They just gave the load balancer more victims. This is the trap. Horizontal scaling hides the real bottleneck behind a health check smokescreen. When a pod crashes and restarts, the load balancer briefly sees it as unhealthy and keeps traffic away. By the time the pod is running again, out-of-memory logs get buried in a sea of container restarts, and the on-call engineer sees latency spikes, pods restarting, and reaches for the lever that worked last time. More replicas. It's a natural instinct. It saved you before, but here it's exactly the wrong move. The sharp dividing line is resource profile. If the instance burns CPU proportionally to request rate and memory is flat, horizontal scaling is your friend. If the instance's memory footprint per worker thread is large, or worse, grows with concurrency, then widening the pool of instances doesn't widen the per-instance runway. It just multiplies the total memory bill while giving each instance the same tiny margin. You might even make things worse because the load balancer's health checks keep restarting pods and the constant cycling burns CPU for nothing. Let's make it concrete with a container orchestration example. A typical Docker Compose setup might declare a web service with a memory limit of 256 megabytes and 3 replicas. The application starts fine because idle footprint is 200 megs, but a single user-triggered search constructs a huge response and pushes the process to 260 megs. The kernel kills it. Adding more replicas with the same 256 megabyte limit won't stop that search from blowing past the ceiling on whichever replica handles it. The fix is to raise the per-container memory limit, say to 1 gigabyte, and then decide whether you still need 3 replicas. That's vertical scaling. You're giving each instance more headroom. In Kubernetes, the same trap shows up in resource limits. A pod that requests and limits 512 megabytes will be evicted the instant it exceeds 512, regardless of whether the node has free memory. Scaling the deployment from 3 to 10 replicas won't stop an individual pod from crossing its own limit. Often the right intervention is to profile memory usage under representative load, then raise the limit to something like 2 GB while keeping the number of replicas constant, or even reducing replicas because you no longer need as many to handle the same traffic when each pod can stay alive through bursts. There's a hidden cost angle too. When you horizontally scale a memory-constrained service, you multiply the idle memory cost. If one pod idles at 3.4 GB and you run 10 of them, you're burning 34 GB of cluster memory before you've served a single request. Vertical scaling, say one pod with 34 GB of RAM, can be dramatically cheaper in cloud environments where you pay for reserved memory per host. It also avoids overhead like connection pooling, intra-cluster replication, and load balancer state that each extra instance brings. So, when should you use which? Horizontal scaling dominates when the work is embarrassingly parallel and memory per request is small and bounded. Think serving static assets, crunching image thumbnails, or handling stateless API calls with lightweight JSON. Vertical scaling shines when you have a memory-intensive baseline, like a large data set cached in RAM, a JVM with a fat heap, or a machine learning model that must be loaded into process memory. It's also the right call when you hit a hard limit on per-instance memory that no amount of sharding can lower. A good rule of thumb: if adding a second identical process on the same machine would double your throughput because it uses a second CPU core, you have a horizontally scalable workload. If adding a second process on the same machine would double your memory consumption without doubling throughput, because the bottleneck is a single memory-hungry data structure, you need a bigger process, not more processes. The most dangerous moment is when your monitoring shows high memory usage and your load balancer shows higher request rates. Your brain sees the load balancer metric and defaults to, we need more capacity, so more instances. But the memory graph is telling you something different. The existing instances are starved. The production lesson I learned the hard way is this: before you scale out, always check the per instance resource saturation. If every instance is above 80% of its memory limit, adding more instances won't lower that percentage. It will only duplicate the same precarious state. The fix is to give each instance more breathing room, vertically with a larger limit, and only then decide whether you still need extra copies for fault tolerance or peak throughput. Pulling back, the load balancer isn't the enemy. It's a brilliant tool for distributing work. But it's also a master of disguise. It makes a memory-starved service look like it just needs more copies. Understand the difference between a per-instance bottleneck and a concurrency bottleneck. When you see restarts and out-of-memory kills, the answer might not be more containers, it might be bigger containers. That's the load balancer trap. Avoid it, and you'll save months of expensive debugging and thousands in wasted compute. Thanks for watching. I hope this one was useful. See you in the next video.